today's video. Today, in this tutorial, we will attempt to both build the intuition for and construct a neural network in under 10 minutes. Let's get started. First off, it's important to understand what constitutes a neural network. Neural networks fall under the area of deep learning, and a neural network attempts to solve a given pattern recognition problem without any prior knowledge of the subject area. For example, if we train a neural network to classify between images of cats and dogs, the network would initially have no knowledge about distinguishing between cats and dogs. Simply put, the structure of a neural network is several layers of nodes. These interconnected nodes usually are packaged in layers. A neural network typically has an input layer and an output layer. Between the input and output layer, we stack several hidden layers, which do matrix multiplication and computation to calculate the outputs based on the inputs. Neural networks are thought to be inspired by neuroscience and the concept of neurons and their synapses. Now let's talk about how neural networks actually work. Neural networks start with some number of inputs, with each input having a specific weight or parameter which defines its importance in the model. We take the linear combination of each input with its weight, and we calculate the sum for all of our inputs. Usually, most networks also have some kind of ingrained bias or value offset. After we find our sum, we apply what's known as an activation function. This is a mathematical function which introduces nonlinearity into our network. I'll give an example later. After applying the activation function, we reach our output, or the final value that we desire. So just to review, in a neural network, we have a certain number of inputs with their respective weights. We sum the products of these inputs and weights as one neuron, and we apply an activation function to introduce nonlinearity across all of our neurons. We also typically have what's known as a learning rule. The learning rule is essentially the logic of our network, and allows the user to essentially tune and adjust the values of the network. In other words, shifting the weights and the bias. Let's talk more about what an activation function is. As I said earlier, an activation function is an example of a technique used to integrate nonlinearity into our problem. Datasets in the real world are never black and white, and typically they show nonlinear behavior. In other words, you can't separate classes with a simple linear line. Activation functions allow us to solve this problem. A classic example of an activation function is the sigmoid function. So now, how do we train a neural network? To physically train a neural network, we use a process known as backpropagation. The goal of training a neural network is to reduce the average loss or the error across the network. And backpropagation is a technique that allows us to reduce the loss by adjusting the connection weights of our network. It is also interesting to note that the math behind backpropagation uses the derivative chain rule. So that's how it mathematically works. So to summarize, neural networks are trained by a weight update that's also known as backpropagation. So, as I said earlier, we're going to build a neural network in this tutorial. So now let's get to coding a neural network. Some of the precursory code for the building of our neural network. I've already imported some libraries like NumPy, Seaborn, Matplotlib, Pandas, etc. And these are some of the libraries that are useful for data pre-processing. This is not really important to the building of our physical neural network algorithm, but these are important to process the data that we plug into that neural network. So as you can see here, after importing the libraries, I then imported a .csv dataset for diabetes data. And I split it into X and Y, training and test data. And I was able to split it using the scikit-learn train test split module. So now that we've defined our data, we pre-processed it, let's now define the layers of our network. I'm going to start by importing the sequential Keras layers. So we're going to say from Keras, we import sequential. Today we're going to be building a simple 3-layer sequential model. So this is necessary for building that neural network. We're also going to say from keras.layers import dense, because we're going to be building a 3-layer neural network today, and all the layers in our network will be dense layers. So now let's define our classifier, and our classifier, as I said earlier, will be a sequential deep learning classifier. So we're going to say classifier equals sequential per boom. So there we go. So we defined our classifier. Let's start adding our layers. So we're going to create a simple 3-layer network that uses 2 kind of activation functions. The first activation function that we're going to use is ReLU, or rectified linear units. we're also going to be using the sigmoid function activation function. And so all of our dense layers will be applying a kernel operation as well. So let's start by defining our input layer. We're going to say classifier, the name of our network, .add, the dense layer with size 4, and the activation being ReLU. We're also going to initialize a kernel. This is kind of the feature map of our model. So we're going to say kernel initializer equals random normal. And since this is our input layer, we have to specify the input dimension. So we're going to say input dim equals 8. Perfect. So we've added the first input layer. Let's add the layer between input and output, the hidden layer. We're going to say classifier.add, another dense layer of size 4. The activation will once again be ReLU. And we're going to initialize a kernel again. So this time the kernel initializer will be the same. It will be random normal. So let's add that. Kernel initializer equals random normal. And this time we don't actually have to specify our input dimension because this is a hidden layer. And since it's not the input layer, there's no need to put input dimension equals x. So there we go. We've coded our hidden layer. And now for the final layer, our output layer, we're going to add another dense layer. So we're going to say classifier.add a dense layer of this time size 1, because we only want one neuron in our output layer because we want one final classification. So that's why in our output we have one layer, or one size. We're going to this time define our activation as sigmoid. And the sigmoid function is a classic activation function, and our kernel initializer will once again just be random normal. Perfect. Alright, so we're set with our layers. So now that we've added our layers, we can compile our network. We will be able to compile our network with the atom optimizer, and we can gauge the error with the binary cross-entropy metric, alongside the metrics of accuracy. So let's compile our network. We're going to say classifier, our network, the name of our network, .compile, and we're going to say optimizer equals atom. We're also going to define, and we're also going to say loss equals binary cross entropy. And we're also going to finally define our metrics that we're going to use for evaluating accuracy as just simply accuracy. And there we go, we've compiled our classifier. The final step in this process is to now fit our network to the dataset. So we can accomplish this by the method known as the fit method. We will use a batch size of 10, and we can do 100 training runs, and in other words, we can have 100 epochs. So let's fit our data, our diabetes data set that I've already pre-processed, to this 3-layer network. We're going to say classifier.fit our X training data, our Y training data. We're going to say batch size equals 10, and we're going to define our number of training runs or epochs, and this will be 100. And perfect, we fit our data to the classifier, or in this case, the neural network algorithm. And there we go. We have just built a really simple yet powerful neural network with the Keras library. And at the same time, we've also decoded complex concepts like back propagation and activation functions. And so overall, just thank you for watching this tutorial, and make sure to like and subscribe if you want to see more content like this in the future. I hope to see you next time, and thank you very much, and goodbye.